Okay, so if we're working a problem that has a collision or something where we can say that momentum is conserved, we got to look at the problem a little bit deeper because we might need another equation, and we can do that depending on the type of collision. So we have what's called elastic collisions. Go ahead and think of a bouncy ball or something, right? Something that's purely elastic loses no energy. No energy. So if it is purely elastic, it loses no energy. We go to the far end of the spectrum and we can call the type of collision an inelastic or plastic collision. Meaning, when the two objects collide, they actually move off together as one. In this case, energy is lost. And there's everything in between, right? Actually, everything is typically in between because we always lose energy of some sort. If we're going to do a problem where we have a ballistic pendulum and it's just a block of some mass of wood or something, and you fire a bullet into it and it gets lodged in there. That's an inelastic collision. That's a purely plastic one. We can, in that case, we get to say that our momentum initial is equal to the momentum final. So we have two objects. We have the mass of the bullet, so I'll call that little b, and the mass of the block. And we can go ahead and say m1v1 initial plus m2v2. Let's call it bullet. M lowercase b, velocity of the bullet initial, plus the mass of the block times the velocity of the block initial is equal to its final state. Alright, that's a mouthful. So what do we have here? Momentum is conserved, and we can say that they move off together at the same velocity after the collision. What does that mean? That means that these two things are the same, and we can just call it some V final. What that allows us to do, and this doesn't have to be a ballistic pendulum, it could be the big semi-truck hitting the little tiny car, or a person or something, right? That's why these accidents are so tragic. It barely slows this semi-truck down, and it basically just adds this mass to the semi-truck. So they move off together as one combined mass. And I'm sure you've seen an accident, or the remnants of an accident, a car accident, where the cars are literally combined into two. That's what's happening. That's a nearly purely elastic or inelastic collision, or plastic collision. But of course, energy is lost. If it made a bang and some noise came out, energy was lost. It got warm from two things hitting each other, energy was lost. But we can still do a pretty good rough estimate with this right here. So I'm going to substitute V final in for these two terms, because they're going to move off at the same combined velocity. What we get, and we can actually go ahead and cross out, oh, it's not a plus sign right there, velocity of the block initial. The block is typically hanging at rest in this case. It doesn't have to be, but we can cross that out if we wanted to. I'm going to go ahead and leave it as a general case where they move off together with some combined velocity. So now let's solve it for that. We get the final velocity, if it's a purely elastic collision, is equal to, in this case, the mass of the bullet times the velocity of the bullet initial, plus the mass of the block, plus the velocity of the block initial, all divided by the combined mass, because we could have factored this out to be the mass of the bullet plus the mass of the block times V final. Like that. So when I divide through by this term, I get the mass of the block, or the bullet, plus the mass of the block. And that was just for that case. It can be any two objects, right? M1 V1 initial plus M2 V2 initial, all divided by the combined mass, M1 plus M2. You might sometimes see M1 plus M2 as a capital M, but it's a pretty powerful equation right here. All comes from the conservation of energy, or the conservation of momentum. Now, like I said, most collisions are somewhere in between. We're going to be pretty much doing one or the other for simplicity. But the next lecture is going to go over what happens if energy is conserved. Guess what? We have conservation laws for that. So we're going to say that 1/2 mv initial squared for the first mass plus the second mass, and that's where we're headed. And then we'll look at two dimensions, and that'll wrap us up.